How's it going, everyone? Welcome to today's video. For this video, we're going to talk about the concept of molarity. And when we're talking about molarity in chemistry, we're talking about the concentration of a particular substance that is dissolved in a liquid. This is typically used for acid-base chemistry when we're trying to figure out, the concentration of this acid in this particular base. But it can be used for anything that is dissolved in a liquid. We do this because normally in stoichiometry, or as we've done in previous videos of stoichiometry, we are only dealing with the mass, the number of grams of a particular substance that is reacting with another substance. And we use that information using the molar mass that we can get by looking up that molar mass for that particular substance, or just looking at the periodic table, and then doing stoichiometric calculations to figure out how much that would produce of two different other substances, or how much you need of a substance to make that reaction go to completion. In this case, it's a lot harder to do that when you have liquids. It's harder to weigh out the mass, subtract that mass that should be just water, figure out the mass of the other substance, when we can just use a molarity calculation. That is, if we know the concentration of something, but we don't know the concentration of another thing, we can use this information to figure out what the concentration is of that other substance. In this case, we'll look at a couple examples of sodium hydroxide and hydrochloric acid. Okay, how we do that using molarity is we take the number of moles that we know is within a liquid, divide it by the number of liters that substance, that number of moles is dissolved in or resides in, and that would tell us that concentration. Alternatively, if we knew other information, that is, if we knew the molarity and the volume of a particular substance, we can use this information to find the moles, and other math just using this equation to figure out information we might need to do some stoichiometry and other applications of this. Now let's go ahead and look at our first example. Okay. To look at our first example, just to kind of explore how we would use this equation in chemistry. Something that is often used in chemistry, especially during acid-base titrations, is sodium hydroxide. An example of what might be used is 1 molarity sodium hydroxide, and something we might try and figure out is if we used so many liters of 1 molarity sodium hydroxide, is how many moles would be in that particular sample that we're working with. Now, this number is really small. Keep in mind, liters are really big things. I think of it as there's those 2-liter giant bottles of Sprite that you can get at the store. Half of that would be 1 full liter. So we don't normally use big numbers like that or big amounts like that in chemistry when we're just doing small things, unless we're really doing something on a bulk scale. So that's why the number appears small. So if we want to try and figure out how many moles would be in this sample of sodium hydroxide at this concentration, we would just, let's write out our equation. M equals number of moles per liter. Now that is 1 molarity is equal to the number of moles per 0.05 liters. Just multiply by both sides, times 0.05, and then that comes down to, it's just 1 by itself, so 0.05 right there. So that would say that at 1 molarity of sodium hydroxide, if we had a sample of 0.05 liters of that sample, we would also have 0.05 moles of that sample, or of that substance dissolved in that sample. Let's do one more example, and then we'll take a look at what that looks like in practice. Okay, another example is, say we knew the number of moles that was in a given sample, and we knew the volume of that particular sample. And we want to try and figure out what the molarity was. And this is just a simple plug-in right here. Same thing as we did before. Just write out your equation so we know what we're working with. The molarity equation to figure out what the concentration is, or the components of it that make up that concentration, is M equals N over L. We would plug in our information here. N, we have 0.025 moles per 150 milliliters. you would do is just go top divided by the bottom, and I'm going to math this really quick. 0.025 divided by 0.150. And that would make this molarity 0.17 rounded. Sorry, I'll use significant figure people if I was off there by a little bit. So that would be our molarity here. That would be our concentration of hydrochloric acid that we would have in this given sample if we knew that it contained 0.025 moles in 150 milliliters, or 0.150 liters. Let's go ahead and take a look at what this looks like when in practice, like if we were actually doing some stoichiometry. Okay, for this example that we're going to look at, we'll just look at one example because this really is just a short skill to learn for chemistry. Something that is often done in a chemistry lab is a titration. We take a known sample of something we're working with, in this case sodium hydroxide, and we're using that in a titration to do a neutralization of an acid, in this case hydrochloric acid, that we're not quite sure what the concentration of it is, either because we mixed a bunch of stuff together and we wanted to make sure it was there, or we were trying to make something very specific to a certain molarity, and we were using this to try and figure out to that precise degree if this is the right concentration that we want. So we take 1 molarity sodium hydroxide, and we use 1 molarity just because, you know, it's a nice even number. You would see concentrations of maybe 0.1 molarity, or even less, I guess, if you can do that to, you know, save on sodium hydroxide, but to each their own. In this case, we would take a volume of something that we know. So if we were doing a titration, maybe we'd put 50 milliliters into a beaker. So we know what the volume is of this. Now all we need to do is figure out how many moles would be in this volume of this concentration. We could do that by doing some stoichiometry. So we would take our burette, we add some sodium hydroxide slowly into the beaker filled with about 50 milliliters of this, and just slowly adding until we reach that point of neutralization. And say we got to a point where it was, we added 23 milliliters. Oh God, this is supposed to be 0.023 liters of sodium hydroxide into that sample that contained 50 milliliters of hydrochloric acid. From there, we use the molarity equation. M equals, this is our volume here, our liters, so it goes N over L. So we don't know the N. Here's the L. That is the same as 1 equals N, let's get rid of this really quick, over 0.023. Multiply both sides by 0.023. Oops, 0.023. And that comes out to the same thing. N equals 0.023. We like to use, and it's good to use something that's got a nice even number like that, because then when you get this, you know it's going to be that same number of moles. So it's 0.023 moles. Now, once you've reached this point, then you just take a look at the equation here, the chemical equation. So it takes 1 mole of hydrochloric acid for every 1 mole of sodium hydroxide to be made. And I really should get rid of these here. Put them up here. So we don't know the molarity of this. This was a 1 molarity. I apologize if that confused some people. So these react in a 1-to-1 to 1-to-1 ratio. We're not even looking at any of that. So for every 0.023 moles of this, 0.023 moles times 1 over 1, that gets us, well, same thing. It's 0.023. Now that we've got the number of moles and we know the sample here, the sample size of our hydrochloric acid, we can use this information to figure out the number of the molarity, the concentration of this hydrochloric acid, so we can use it for future experiments. Let's go ahead and do that. So molarity is equal to N over L, and I just do that out of habit. So that is also equal to 0.023, N for moles, number of moles, divided by 0.050, and that would come out to 0.023 divided by 0.050, almost 0.5 molarity, 0.46 molarity right there. Now, I don't know why anyone would specifically want 0.46, but now we know. If we need to add a little bit more there, we could do that. There's also another equation you can use to figure that out. You know, what concentration you would need, how much you would have to add, and we'll talk about that in another video. Thank you so much, though, for watching this video. I hope you found it helpful. Sorry if it kind of dragged on maybe a little bit there. It seemed kind of disorganized, but if you liked it, if it helped you out, leave a like, subscribe to the channel. It helps a lot, and I will see you guys all in the next one. Take care.